Quick question. What is the coldest planet in our solar system? If you said Neptune, you're wrong. Don't feel bad. Almost everyone says Neptune. It's the farthest planet from the sun. It seems obvious. But the coldest planet is Uranus, the seventh planet, the one closer to the sun, the one nobody talks about. And the reason Uranus is colder than Neptune, despite being closer to our star, reveals something deeply strange about what happened to Uranus billions of years ago. Something violent, something that changed it permanently, and something that scientists are still trying to fully understand today. This is not a story about which planet is colder. This is a story about a catastrophe and what it left behind. Let's start with the numbers, because they're genuinely weird. Neptune orbits the Sun at an average distance of about 4.5 billion kilometers. Uranus orbits at about 2.9 billion kilometers. Neptune is roughly 1.6 billion kilometers farther from our star. By every intuition we have about heat and distance, Neptune should be colder. It receives less sunlight. It has less energy input. It should be the frozen edge of our solar system. And yet, Neptune's average temperature around -214 degrees Celsius. Uranus's minimum recorded temperature -224 degrees Celsius, 10 degrees colder consistently. This has puzzled planetary scientists for decades. A planet closer to the sun, receiving more energy, runs colder than its more distant neighbor. If you designed a solar system from scratch and wanted this to happen, you'd have to do something very specific to one of the planets, something irreversible. To understand what that something is, we need to talk about where planetary heat actually comes from, because it's not just the sun. Here's something most people never learn in school. Every planet in our solar system is still warm from being born. When the solar system formed 4.6 billion years ago, rocks, ice, and gas were colliding at incredible velocities, merging into larger and larger bodies. All that kinetic energy, all those impacts, converted into heat. Heat that got trapped inside each planet. And that heat is still there, still radiating outward, still influencing the temperature of each planet's atmosphere. Earth radiates about twice as much heat from its interior as it receives from the sun. Jupiter radiates nearly twice the heat it receives, Saturn even more. And Neptune, little cold Neptune at the edge of our solar system, radiates 2.6 times more heat from its interior than it receives from sunlight. That internal heat warms Neptune's atmosphere from below. It drives its winds. It keeps Neptune warmer than it should be. So now the question changes. The question is no longer, why is Uranus cold? The question is, why did Uranus lose its internal heat? Or more precisely, why is Uranus the only planet in the outer solar system that barely radiates any internal heat at all? Uranus is the calmest looking planet in our solar system. Where Jupiter has its great red spot and violent cloud bands, where Neptune has the fastest winds ever recorded in the solar system, reaching 2,100 kilometers per hour, Uranus looks almost featureless, a pale blue-green sphere, smooth, quiet, almost boring. And that calmness is the clue. Uranus emits almost no internal heat. Measurements from Voyager 2 and subsequent telescopes show that Uranus barely radiates more energy than it receives from the sun, a ratio of approximately 1.06 to 1. Compare that to Neptune's 2.61 to 1. Uranus has almost completely lost, or is completely trapping, its primordial heat. No other planet in the outer solar system behaves this way. The internal heat that drives weather, winds, and atmospheric circulation on every other giant planet is essentially absent on Uranus. The planet is thermally dead, or close to it. But why? There are two leading theories, and neither one is fully settled. The first involves a catastrophe. The second involves a trap. Uranus is the only planet that rotates on its side. Every other planet spins more or less upright relative to its orbit. Earth is tilted 23 degrees, that's why we have seasons. Mars is tilted 25 degrees, Saturn 27 degrees. Uranus is tilted 97.77 degrees. It rotates almost perfectly on its side. Its poles face the sun directly, one for about 21 years at a time. This tilt is not natural. You cannot get a 98-degree axial tilt from normal planetary formation processes. Something hit Uranus, something large, at least the mass of Earth, possibly several times larger, struck Uranus with enough force to knock it sideways billions of years ago, and it's been rolling on its side ever since. Now, could that same impact explain the missing internal heat? Possibly, in two ways. First, the impact itself may have blasted away a significant portion of Uranus's original heat. A massive collision releases enormous energy, but some of that energy escapes rather than being retained. And second, more likely, the impact may have fundamentally disrupted Uranus's internal structure, creating a stable, stratified interior where denser materials sank and lighter ones rose, forming invisible barriers that prevent heat from circulating outward. Think of it like a flask of hot water sealed inside a box. The heat is still there, trapped, but it can't escape. Some models suggest Uranus may actually have a hot core buried beneath an insulating layer of ice and gas that the impact rearranged. The planet isn't cold inside, it just can't release what it has. And that distinction changes everything. The second theory doesn't require an impact. It requires a different kind of interior. Uranus is classified as an ice giant, not because it's covered in ice, but because its interior is rich in water, methane, and ammonia under enormous pressure. These materials behave differently from the hydrogen and helium that dominate Jupiter and Saturn. One hypothesis suggests that under the specific pressure and temperature conditions inside Uranus, these materials formed stable, stratified layers that simply don't mix or circulate the way Jupiter's and Saturn's interiors do. If this is true, then Uranus's heat isn't gone, it's locked, sealed beneath stable chemical layers that act as thermal insulators. The planet is quietly holding billions of years of stored energy in its interior, unable to release it. From the outside, it looks cold. From the inside, we have no idea what's happening. The honest answer is that we don't know which theory is correct. Possibly both play a role. Uranus has only been visited once, by Voyager 2 in 1986, a flyby that lasted hours, from which we're still extracting data. Uranus takes 84 years to orbit the Sun, and because it's tilted 98.77 degrees, each pole spends roughly 42 years in continuous sunlight and 42 years in complete darkness. When Voyager 2 visited in 1986, the South Pole was pointed almost directly at the Sun. That pole had been in continuous sunlight for over 20 years. You'd expect it to be significantly warmer than the equator or the dark pole. It wasn't. The sunlit pole was barely warmer than the dark side, a hemisphere that had been bathed in sunlight for 20 years, barely measurably warmer than the hemisphere that had been in darkness for the same period. In any normal planet, you'd expect a significant temperature difference between a hemisphere that's been in sunlight for 20 years and one that hasn't. On Uranus, you don't get one. The atmosphere distributes temperature so uniformly that even 21 years of direct sunlight barely makes a dent. This tells us something profound. Uranus is not being warmed from below. The circulation patterns that would create temperature differences, the convection driven by internal heat, simply aren't there. The planet is thermally inert, in a way no other planet is. We've known Uranus is the coldest planet since Voyager 2. That's almost 40 years, and we still don't fully understand why. The impact hypothesis is compelling, but we have no direct evidence of the impactor. The layering hypothesis is plausible, but we can't probe Uranus's interior. Both could be true. Neither might be the complete picture. NASA and ESA have been discussing a Uranus orbiter mission for a decade. In 2023, the National Academies of Sciences ranked Uranus as the top priority for planetary science for the 2030s. Not because Uranus is the most spectacular planet, but because it is the most mysterious. The planet that doesn't behave. The one that rolled onto its side and went cold, and has been quietly refusing to give up its secrets. Most questions in planetary science have answers. We know why Mars lost its Most planetary science questions have answers. We know why Mars lost its atmosphere. We know why Venus is a hellscape. We know why Jupiter has its great red spot. But Uranus, the planet everyone forgets, the one that barely comes up in conversation, is sitting at the edge of our solar system with one of the strangest thermal profiles in astronomy. Cold, tilted, quiet, holding its heat like a secret. The next time someone asks you what the coldest planet is, you'll say Uranus. But more importantly, you'll know that the interesting question was never which planet is coldest, it was why. And that answer is still being written.